The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to today's Tech Talk on building pressurization, pitfalls, and solutions. My name is Sherry Adams, and I will be moderating for today's session. Please note that throughout the Tech Talk, all phone lines will be muted. This will minimize any background noise and feedback that could distract from the presentation. When you first joined the Tech Talk, an attendee control panel appeared on the right side of your desktop. On the left side of this control panel is a small tab with an arrow icon at the top. Pressing this icon allows you to minimize and maximize the control panel. When maximized, you could use that panel to submit questions. We will be gathering questions throughout the presentation and we'll leave some time at the end for Q&A. If your question is related to a particular slide, please include that number of the slide in your question. And as always, a PDF of the slides from this presentation will be sent out electronically to all those who are registered for today's Tech Talk. We will also be recording it, and it will be available on our website under the resource section. The new password to access the Tech Talks is TechTalks 18. Today's Tech Talk is from John Villani. John is currently the president of the BCA and vice president of Grumman Buckus Associates. So John, I am going to turn this over to you.
Excellent. Thank you, Sherry, and thank you all for joining. This is a Tech Talk, part of our Tech Talk series, which is a member benefit. So just one of the ways we are trying to give back to you as the members, bring you value for the association, and talk about things that are hopefully relevant in your daily business and commissioning and providing commissioning, being involved in commissioning. So with that, we're talking about building pressurization today, kind of a common theme that we're seeing much more of in the control sequences in our building operation, something that we're paying much more attention to. So just getting a few things out of the way. I'm not going to spend a lot of time here, but one of the aims that we've hoped for in the Tech Talks is definitely for boots on the ground members of commissioning teams, be it providers, owners, etc., contractors, that we get some of the younger staff trained and educated. So in the theme of that, units of pressure and conversions, giving a little bit of history here and data, things you may see. So we refer to pressure in PSI, inches of water column, water gauge sometimes. We refer to it in feet of water often. Occasionally you'll see inches of mercury, not real common, but just if you see an inch Hg, you'll know what that is. I'm going to say very rare, but every once in a while you may see that. And then you need to have an understanding of the conversion between PSI and feet. This is typically much more going to be on the water side, so I'm giving that over on the right just for engineers to know about. Make sure you kind of commit that to memory. That's a very important one. Touch on that in a little bit. So for air, things you're going to be using to measure air, and these are a few of the types of equipment we have here at GBA. Very common and standard in the industry. There's a few other manufacturers that make things certainly, but these are a few of our tools. So the short ridge ADM, magnehelic gauges, you can see that one is sitting firmly at 1 inch of water gauge. That's me actually, I think, blowing in that. And then we have our one of our Dwyer manometers. Same thing. That's sitting at 2.26 inches water gauge. You can see that if I get my little highlighter thing over here. Somewhere right around here it says inches water gauge. So just some tools that you may need if you're dealing with building pressurization. Oh, how do I delete that? Bear with me a second. Erase all drawing. There we go. Sorry about that. And go back to my normal. Okay, there we go. Sorry. Tools for water. Here's a couple of the tools that we have for water. So hydro data meter, hobo data loggers. This could actually do air or water. We've got pressure gauges, etc. So just a few backgrounds. And the last little caution here, if you're doing water, not really, we'll switch out of water here. We'll get to building pressurization. But if you're doing water, be careful where your contractor might do the hydro test. True story. We had a 26-story building. When you added the penthouse, the basement, etc., we were about 28 stories. at about 13 feet a story. So when you do the math, that comes to 364 feet divided by 2.3 feet per PSI, comes to 158 pounds. Unfortunately, they did the specified specification of 150-pound test pressure at the top of the building, giving us over 300 pounds in the basement and blowing out the copper piping, making a big mess. So just be careful on that little side. Again, Tech Talks are all about tips, real world stuff. So building pressure. What pressure is expected? And this is hopefully going to be a little bit of a little question here, Q&A, hopefully get you guys thinking about it. 1 PSI, 1 inch water gauge, what and where does the building pressure come from? So it's really important to kind of think about, and this is hopefully going to dial you in to answering this question, okay? And where does building pressure come from? What is generating the pressure? Hopefully you guys are knowing this answer, but the air pressure for building pressurization comes from the air handling systems. So the air handlers are where we get the building pressure. That's what's causing pressure in your building. I use water column here. Another reference. I'm using a few different metrics here. This is talking about the air handler. First of all, what is the static pressure that we typically refer to? What does the air handler run at? And a lot of times you're going to hear this magical 1.5 inches is the static the air handler runs at, which is actually not static. It's actually a differential pressure between the pressure in the duct to the pressure outside the duct. And you'll see this 1.5 inches as a set point. Very, very, very common. And my big hint here is 99% of the time that means it has not been set up properly. So if you're a commissioning person, you walk up to the BIS, you ask the tab contractor, what's the set point? And he goes, oh, 1.5 inches. Most of the time that will not be the proper pressure that is the most energy efficient, we will say. And that you have to find that through tab and the commissioning process to drive all the boxes open, figure out how much air you actually need to get the furthest or most remote boxes to have enough air for them to meet their set point. So the air handler is where pressure comes from for you to be able to pressurize your building. So what is the pressure that we're looking for building pressure? And for those of you that know me, I like to do lots of hospital projects, so I use this as a reference point, maybe help you commit this to memory. This is the code for operating rooms coming from ASHRAE Standard 170, that an operating room must be at least 0.01 inches positively pressurized. Well, that's giving you a clue, 0.01 inches. It's a very, very, very small number. Building pressurization is going to be very small. Okay, so operating rooms, I say, are typically controlled to 0.01 to 0.03. Buildings, here's your answer. Building pressure is typically in the 0.01 to 0.05 range is what you're going to be typically looking to see. Set point, probably 0.03, 0.05 type of numbers. So that is what you're shooting for building pressurization. It's not 1 inch, it's not 1 PSI. Those would be values that are way, way out of range. So giving you a bit of a building envelope perspective, I want to talk about that. So I know lots of folks are mechanically inclined, myself included, but as the building envelope commissioning world has come into full steam and full speed, and we are engaging in almost all of our projects with some level of building envelope commissioning, it's really important as they tighten up those buildings or endeavor to tighten up those buildings that we're looking at some of these numbers. So this just happens to be 2 different projects my friends at Intertech had worked on and shared some data with us where they tested the actual whole building leakage rate. And I won't go through all the numbers, but I want to just give you an idea of two different extremes, and that's the bottom number there, leakage rate, CFM per square foot at 0.05 inches water column, water gauge. That is so the building was pressurized to that amount. And in the left building, a very poor example was leaking 0.2 CFM per square foot versus 0.027 CFM per square foot. So the building on the right there is extremely better. Even though different costs, different types of air barriers, etc., the buildings are not exactly the same size, etc., but just want to highlight that as we start focusing. And the building on the left had I think no commissioning, building envelope commissioning whatsoever. Building on the right did have building envelope commissioning. So by having building envelope commissioning and a methodical process, they were able to tighten up the building, therefore reducing that leakage rate. Now again, I'm going to go back to what I just said a moment ago. Where does all that leakage come from? It comes from the air handler. Well, we're going to get to another slide, and we're going to see where that, within the air handler, where does the air come from? And you know, the spoiler here is it comes from outside air. So if you're in an environment with, you know, lots of hot, lots of cold, you're going to need to have extra outside air to create a positively pressurized building. And if you look at these two buildings, it starts to give you an order of magnitude that shows you how extreme and how much more outside air the building on the left would actually need to be positively pressurized. The other piece down at the bottom, Ashley's got a nice little quote here, and it's something that we do a lot of in sequences of operations, is we look at having an unoccupied mode or scheduling things off. Well, Ashley goes and talks about, you know, when you dial it all in and you get it perfect during normal business hours, you may, you know, think, okay, I'm good. Well, when you go unoccupied and the building does something different, have you lost that building pressurization? So if you are looking at building pressurization and that's part of your sequence, part of your focus, part of functional testing, make sure you're looking at the trends during the off hours, because that's where they say unoccupied mode pressurization is lost, infiltration, and potentially moisture intrusion may be significant. So important pieces. Hopefully I'm hitting on things for you to think about and remember. One of the things when we talk about building envelope is a lot of times people talk about stack effect, and bear with me, I need to click, I forgot. This has animation. There we go. All right, so the stack effect is something that you're going to find in buildings predominantly in your northern cold climates that happens in the winter, where cold outside air wants to come in the bottom of the building and warm air is naturally going to gravitate up and go out the top of the building. There's lots of pictures with buildings with the windows open at the top of the building because they're hot. And it's in the middle of the winter and you see snow and things of that nature. So one of the questions that we've seen and dealt with is, well, how do you combat that? So a couple of things you can do, a lot of them have to do with architecture. They have to do with the building envelope and basically trying to have a very sealed floor-to-floor building. So you mitigate the pathways for air to move up and through the building. So when you're looking at the fire stopping and the shaft ways and all of those places where air can move up the building, that's kind of one of the biggest things you need to deal with and start there. You can even look at, you know, revolving doors instead of just single doors or sliding doors at the base of the building. So lots of architectural solutions, vestibules make a big difference to try to mitigate and stop that. Mechanically, one of the things to look at is how are you pressurizing the bottom of the building? You may need to look at adding additional pressure by increasing the outside airflow at the base of the building to try to combat. So you're almost trying to overpressurize that basement. The problem with that is, what was the air handler designed for? If it was only a 20% outside air sort of unit, then you want to start bringing in 50%, 60%, 70% outside air in the winter. You may not have the heating coils to do that. So lots of things to kind of address here. It's a bigger issue. Tech Talks are in some ways a little bit of teasers because we don't have enough time to get into everything, but hopefully this is touching on a few things for you to look at. All right. Getting into sequences of operation, and this is going to be where we spend a bit of time now through the rest of this presentation, is examples of this. Bottom line is building pressurization is going to be accomplished with your air handlers, and what I have, if I can do this, let's see, there, my spotlight, that's what I want to do, is right over here. We want to leave air in the building, okay? So the in of supply air to the amount that's returned and exhausted, okay, there's going to be more going in on the supply than what's exhausted and returned. So that is that leftover air, what you leave in the building, is going to be what creates a positively pressurized building. Very simple, the ins and the outs. If you have more return and exhaust, you are going to have a negative building, very simply. So, but a lot of times we find that we don't have a calculation, we don't have a sequence, we don't have the numbers or the math to give us this positively pressurized building. Even though it may be the intent of the sequence, it may be the intent of the project, the intent of the design team, if that's not somehow explicitly given, we don't have a sequence that's going to do that. So I'm giving some of my my tips and tricks of the trade. A lot of times you're going to find you need to leave 10% of the air, okay, of the supply air as a good starting point number of supply air. So whatever that is, if you have a 20,000 CFM air handler, you're going to leave about 2,000 CFM of air in the building. So that's going to be, you know, left in there, so your return and exhaust has to be made sure you take that into account. If this is a fixed exhaust, let's say it's 1,000 CFM exhaust, toilet exhaust, janitor's closets, etc., okay, if you did your supply air minus your 1,000 minus your 2,000, you're now looking at returning 17,000 CFM. So that's where you kind of that math comes into play. And this is your kind of typical air handler screen. Let's dive into that a little bit more. And this sometimes can be done if you have a lot of, actually I'm going to go back for a moment. If you have a project that's sophisticated with lots of air, these are your airflow monitoring stations. We have some of our healthcare projects, some of our university lab projects will have lots of airflow stations, and they'll actually use the airflow stations in the sequence of operations. If you don't have all these airflow stations, this is something you can still do with the balancer and start to figure this out. So what is the low end of the supply fan if you have a VAV system? What does it run at? What is the high end, maybe a midpoint, and you start measuring the amount of supply air. This number may stay the same. If it's a lab project, it starts to get really complicated with hoods, etc. But for argument's sake, we're going to keep this simple and say fixed exhaust. So just your typical toilets, janitors, closets, and some others. So you can start having the balancer look at your return air and saying, what does this offset need to be from one to the other? This is what the written out sequence would start to look at and the way the process would run. So supply air flow is going to be, as always, determined by the amount of static needed to achieve the set point for all the VAV boxes. Fixed exhaust. Now, fixed exhaust is important here. I'm going to pause. It's not all the toilets and all the janitor's closets and all the other things that are exhausting in your building. It's the fixed exhaust for that HVAC zone. So what I mean by that is if you have a small building, 20,000 square feet, and it's got a single rooftop unit, well, that whole building is a single HVAC zone. Take that same building, make it 30,000 square feet, put 2 rooftop units on it. Now in that case, maybe you have all the bathrooms and all the janitor's closets are really on one side of the building, and that becomes your exhausts are all on one side. So one HVAC zone may have no exhaust, and the other may have all the exhaust. So just talking through what I mean by fixed exhaust, you've got to figure out what that HVAC zone is. Pressurization air is going to be typically a starting point of 10%. And I had a caution. I'm going to go back. I want to make sure everyone sees this. Caution, beware of going above 20%. You can start getting your building a little sideways and maybe your measurements aren't great. You want to be careful. This is not something to run away with. If you need 50%, meaning 50% of the supply air has got to be left to make your building positively pressurized, you probably have some other issues and problems going on that you're not going to have a healthy HVAC system getting that extreme. So I have my beware of going above 20%. So we said 10% there. Return airflow is going to be that supply minus exhaust minus the pressurization air. This is what often is forgotten in the sequence. Okay, and again, I'm saying about 10% of the supply airflow is that pressurization air. The recirculation airflow is what actually comes back and recircs from return back to supply, and then your exhaust airflow is these values. So this is kind of that whole thing once again, but I'm just kind of starting with the way this all works. The supply fan is going to control to a static pressure out here as normal. So whatever you find that, whether it's the magical 1.5 inches, 2.3, 1.2, whatever that is, this supply fan is going to track to make sure all the VAVs are happy. Fixed exhaust is specified or measured. Building pressurization has got to be tested, and we're going to show about testing that, okay? But a lot of times the starting point is about 10% of the supply volume. Return fan, now I say calculated. This can also be measured by the tab contractor, and you can start working these values and figuring this out. So if you find you need a certain amount of air here, you can start to then figure out and set the VFD to track off of that, off of a setback difference. So a few different ways there, but you basically somehow need to get the return fan to track to what the supply fan is doing. Or use actual airflow stations if you have live data. And then exhaust, again, is going to be sort of that leftover amount of air that wants to leave the building versus recirculate. Putting this into numbers, and this is a great slide, and I really want to commend, there was an engineer that had done this, they'd put their graphic together, and really what I want to commend them on is there's this balancing matrix at the bottom. Where they talked about the supply CFM, exhaust CFM, so this is their zone, their HVAC zone for air handler 2, their OA damper, return fan, relief fan, return damper. I mean, they gave lots of data. The one shortfall, and actually we picked this up, this was a project that we picked up after it had been constructed, was we looked at this, he said, wait a second, and it's hard to read here, but this is a building pressure sensor right here, and it talks about it's in a corridor. That's the indoor location is in a corridor. But what they had missed was leaving the supply air for building pressurization, leaving some air in there. So when you go through all the numbers down here in this bottom box, what you'll find is they all come out 100% equal. They all kind of wash out. And what I've done up here on the right is to redo their numbers and say, well, building pressurization of 10% of my 1830 would be 1,831. And now we have to come up with a new set point for the return fan. So the return is not going to be the 1831 minus the 910, which would have been your 1740 they calculated. We've got to leave some air in for the building. So we've got 15,569. That's what would have been over here for the return fan. That's how we realized that they had missed that. The sequence said they wanted building to be positively pressurized. They just don't have it in their matrix. So running through these numbers is really important when you're going through this in commissioning and looking at this. Don't expect to find this matrix on most of your jobs. It's few and far between. I'm going to say, as a commissioning person, expect to have to crunch these numbers. To be able to crunch this and look at this, talk to the BAS contractor, feedback to the engineer. This is something that is within your purview as the commissioning professional, to be looking at these numbers, really understanding how your building operates. How are you creating that positive pressure? And one of the things I highlight here on the left, just a little tip, is very often you will see your dampers linked, your outside damper, your exhaust damper, and your recirc damper all linked as a single output with, let's say this guy is the inverse of the other two, meaning if this is 10%, this would be 10%, this would be 90%. Very common to be done. Occasionally that's not going to work, probably a good percentage of the time. If we are not an economizer and we're just in the minnow in this situation, then this may be closed, but yet we need to relieve a little bit of air through that damper. So you can find yourself getting into trouble in that situation. Again, that's an important thing to look at in the design. One of the things, this was a hospital project that they like to have for code a measurement of outside air, so they basically are proving they have the proper outside air. And what you can see here is the minnow has this red box, which is an airflow station. However, we don't have an airflow station on the economizer. And just a word of caution, this is kind of a side tip, that when you do this, as soon as the economizer opens, which is a much larger damper section, you will read below your minimum outside air. It doesn't matter that this damper is 100% open. It has a greater pressure drop than the economizer. So this is one of those where your trending data is going to get a little skewed and look a little weird. Even though, and again, if you're actually trying to measure things and use the measurement of outside air, this would not work at all. Another example, this is an example of just a standard rooftop unit that was on a project of ours recently. We have a space pressure sensor in the design. We have an outside pressure sensor design. So a couple things that we could learn from the Tech Talk. One of the things we missed looking for was in the design is reviewing the locations. Where did the design call out for the indoor sensing location to be? And actually the design didn't have it, so it wasn't there, so it was easy to miss because you just never saw it. One of the things that happened on the building pressurization side for the controls contractor was they didn't have anything to address this outside pressure. Okay, what is the device they're going to use? How are they going to connect up to measure that pressure? And sometimes you have air handlers that come equipped with something, and sometimes they don't. So that was something that they had missed, and then again, they didn't discuss it, didn't bring it up, so we didn't bring it up. This is the sequence. I don't expect you to be able to read it, so I've kind of blown it up there in the yellow box. But I highlight the red text because, again, I really want to enforce the differential pressure. This is called out right in the sequence, that the exhaust fan will modulate the VFD to maintain a differential pressure between the space and outdoors of 0.05 inches. So 0.05. Giving you a really good number, making sure I stress that, of what you should be looking for in your sequences. So they're going to have supply air going in, and they're going to modulate the exhaust to maintain a positively pressurized building. This is a completely acceptable sequence of operations. This should work just fine. Okay, and then don't let it drop below 20%. So If you have a simple project like we did, you don't have a ton of time, you don't have a ton of testing, so you may be going out there and looking at what the contractors have done, and now you're going to say, okay, we're going to implement our functional testing, and they've already got the graphics built. This is a simple, packaged rooftop unit. We take a look at the BAS screen when we get there, and we see this. And what I'm trying to show here is this clouded area I've blown up. It's just an enlargement over here on the right. We see a building static pressure set point of 0.05, just what the sequence says, and we see a building static pressure of 0.25. That is not possible. You will start blowing windows and doors and all sorts of things apart. My building envelope friends would be laughing hysterically here. That is not possible. Don't do that. So we knew right away we had some bad data. We knew there's some faulty things going on here. We were looking at, there's 2 units on this building, an east unit, a west unit, and we start looking at all the trends. And you can see the west RTU is looking very good. That is okay in this range. It's the red data, and then all of a sudden the red data goes crazy, and clearly something is reading wrong. The blue data shows the building was just kind of neutral on their side of not side of the building. So that's kind of what we're looking at here. So we had a couple things going on. Why was the blue basically not measuring any pressure, and then the red was just all over the place? It was also a unit that turned on and off. So trending is super important if you're doing building pressurization. Just another tip there. So where do you measure? Where is this building pressurization measured? Really important you pay attention to this. So on our west unit, that would be this half of the building, the west side of the building, we have our main lobby right here. We have a revolving door, a vestibule, a double door. So a great design to mitigate stack effect, by the way. That's a good design. Vestibules are super helpful. We had a ceiling sensor on the inside of the building, and then the outside sensing location was up at the rooftop unit. So our indoor sensor was here. When we tested, okay, when we were validating and verifying the pressure of the building, we took some long poly tube and we measured from in this lobby area right here, out through the double door, out through the single door, and we had our sensor out here. So when you were doing this in real life and you're conducting functional testing, it's really important to verify this. Okay, you may want to do it at multiple locations. Now this was the west side. The east side, the pressure sensor was in this corridor, and we have a door here and a door here, and there's a pathway, it's more of a service entrance over here to get in and out. So we measured that. Another little tip, you may want to check another corner of the building like back here, meaning you could go into the stairwell, you can go out the door right here. So you may check a couple of the doors, okay, not just one location, especially on a larger building. You want to make sure you've kind of verified that. Now stairwells are a little bit weird, so just be careful of that. Sometimes they have their own pressurization. They don't really get the effect of the building. So it's something to be cognizant of, but you want to make sure you're definitely checking. In this case, our sensing location was in this lobby, was our main one. The shell space, which is this room here, was where they had the poly tube for the indoors rolled up. The problem was the indoor sensor, this was the east side, wasn't even connected. There's nothing in the shell space. We were not putting air into the shell space, just enough to sort of temper it. So that's why that reading was crazy and not registering. Very important you look, and I said this before, the device that the rooftop unit uses to measure the building pressure. You don't want just an exposed poly tube that's subject to wind gusts, lots of weather effects. This happens to be a device by Dwyer. We've seen it. It's been used. It works well. There are others. But I call this out. you want to look for something like this in the controls submittal or the rooftop unit submittal. How are they picking this up? Okay, and measuring that. This is one device. This was the actual control panel here, and this problem with some of our issues, that west unit actually had a failed pneumatic fitting. It was this elbow piece right over here that was failed. It was actually clogged. The elbow was not hollow from one side to the other. That was driving us completely crazy for a while. And I highlight that one of our essential attributes in the BCA is for the commissioning authority to provide constructive input to resolve issues. That is a really important thing. This is not just a checkbox to say, no, it does not work. We worked very hard on that. And what you can see successfully at the very end was our TSI test instrument showing a 0.016 inches H2O water column, and that we were finally getting a positive pressurization. So from that device right there, the TSI, we were actually measuring and teed into the tube that goes all the way down to the lobby of the building. This was a multi-story building, so we were measuring what the system was measuring simultaneously. So that's how you're going to test this. Getting near the end here. For your common rooftop units, your RTUs, one of the things that is almost always done wrong is the balancer comes up with one value with the controls contractor and the rooftop unit manufacturer at startup. And it's almost always the outside air damper will be 20% open is the magical number you will almost always see. Now, in most of our projects, these rooftop units are connected to a VAV system. So they're going to go from peak summer heat, summer cooling to peak winter heating if you're in our northern climate of Chicago. And you're going to see the air handler run all the way up. And then you're going to see the air handler run all the way down on mild days and cool days or occupied, unoccupied modes. You're going to see the supply fan speed going anywhere from 50% up to 100%. The difference here is the amount of outside air that is coming in when the supply fan is varying is not going to be the same. So we had an outside air CFM during the occupied mode of 3,600 CFM. That's the amount that was specified. Well, at 50% supply fan speed, we need the OA damper to be 50% open to be basically close to that 3,600. And what we did is we plotted this chart. We worked with the balancer and we worked with the controls contractor to create this table and basically plot the curve. So when the supply fan got to 58, 66, 74, all the way up to 100%, the outside air damper went from 50% down to what we finally settled on was 22% open. Be careful as you're closing that. Sometimes you get some noise when that damper closes too much. So we actually sometimes had that, and there's a note here, damper was open to prevent whistling. So you can find here that in this value, we actually, for unoccupied mode, we only need 1,000 CFM. Well, the problem was when the supply fan's trying to do a lot of speed in the unoccupied mode, 10% was too low for the damper, and we got a lot of whistling. So we had to override that. And again, this is a complex, adding something much more complex than what you are going to see on a standard RTU. This is a design review question or comment. This is something to work through with your commissioning to address this and look at that. Because most people just do this line right here, 100%, where's my damper to be? And magically, if you look, 20% is a pretty good number for that damper position at 100%. However, it's not at all going to work when you're way down at minimum speed. I think this is almost the end here, and that is the accuracy of your building pressurization sensor. This is a real project measuring real building pressure, and what they installed was a 0 to 10-inch sensor. It was an Ashcroft sensor. Nothing against Ashcroft. Great devices. They sell good things. However, not the right sensor for the application, okay? Because this sensor that we originally had a 0.4% accuracy of the range. If our range is 10 inches, that's 0.004. Okay, so if you look at that range, okay, 4% of that, or 0.004, is going to give you a 0.04 accuracy of that sensor. Now 0.04, we're looking for 0.05 for our building. So if you think about what we want our building to be, this is not at all going to work. So what we did is we had them change the sensor out to a -1 to 1 inch. So that's a total of 2-inch range using the same accuracy of 0.4%. That gives us a 0.008 accuracy. So be very careful. Again, that's a controls review item. You could say that we missed picking that up in the submittal review. In the control submittal, that would be a comment, so we had to have that sensor changed out. The contractor realized it once the math was presented to them. Sherry, that brings me to my conclusion.
Great, John.
Have we got any questions?
Yes, we do, John. We have a few. Well, it looks like this first one might not be a question. Just a note for reference, when a table has both floor area and wall area, it would be helpful for the wall leakage per square foot to be defined to floor or wall area.
Okay, yep. Yeah, I will take that and think that, I believe they're kind of talking about probably this slide here. And I'm going to say, let that go to the building envelope tech talks when they talk about leakage rates. I'm just kind of touching on it here because building pressurization affects it. So I do agree with you. I know from some of my building envelope friends, they talk about 6 sides of the box, which is not always thought about, which would be the 4 walls around the building, plus the roof is the 5th side, but a lot of people kind of forget the basement. And that may be a debatable thing. I will let the building envelope experts debate that, and I will pass on that. But yes, you have leakage of walls, roofs, etc. This is just sort of a summary slide to give you some reference. This is interesting, just as one note here. A lot of times these charts and tables are at a much higher pressure. Okay, this is at a 0.05-inch water column between the inside and outside of the building. So this is at the pressure we've been talking about. This isn't at the something pascals that I'm blanking on at the moment, which is a much higher pressure. This is at actual real world building pressure. So thank you, Sherry.
Thank you. Okay, so the next question is, what has your experience been with pressurizing buildings with return fan systems versus relief fan systems? And then he added, I recently came across a system with a return fan that would draw air in backwards through the relief duct when the return fan was slow to create back pressure in the space. You want the question again? I know I just gave a call.
Yeah, well, it sounds like the return fan's pushing back into the building. So read that one more time, please.
So it's, what has your experience been with pressurizing buildings with return fan systems versus relief fan systems? And then he mentioned he recently came across a system with a return fan that would draw air in backward through the relief duct when the return fan was slowed to create back pressure in the space.
Okay, I'm not sure I'm going to follow that question well enough to answer it, but I'm gonna throw a couple comments here. We're talking about return fans, and quite often the things you have available to you to work on building pressurization, and even on many projects, is you have to do some type of return fan tracking to offset off the supply fan. So again, if the supply fan, bear with me, I'm going to go to that slide. The supply fan is going to maintain static, so it's going to do its own thing. You don't really have control over that. This gets set up if you've done a good job, worked with the balancer. You say, I need my 2.3 inches for this system, so the furthest VAV box on max cooling has enough air. This is sort of fixed. The speed of the supply fan, the amount of CFM of the supply fan is fixed. What this question is referring to is sort of this return fan side, and I think I'm going to simplify it and say the tracking between the two of them. That's something that you can work with the balancer and say, okay, well, how much air am I moving here? How much air should I be bringing back? Should I have and again, just like that table I just showed near the end of the presentation for the outside air damper, you may have to do this multiple times. You may say, let's run to peak cooling. So we need all the boxes, drive them all open, we get our static pressure, and you basically are running at your 100% mode. And then you say, okay, well, how much air do I want to leave in the building? I want to be positively pressurized. What is that offset from supply to return? So I'm going to use some numbers here. I'm going to use percentage. So if supply fan, you say, is running at 90% and satisfying, well, is that offset 2%, 5%, 10%? What is that? So let's just say, for argument's sake, at 100% system capacity, you're running at 90% supply fan speed, and you find I need to be 10% less on my return fan. So it's going to run at 80%. Well, as you drive this system down to its minimum range and set all the VAV boxes to minimum, the supply fan, let's just say, goes from 90% down to 50%. Well, you may find at 50%, this needs to be only 5% less on the return fan. And you've got to take some airflow measurements. So at a minimum, you want to have and work with the balancer and say, give me the 100%, or give me the system down here, the supply side, give me this system measured at 100% capacity and all the VAV boxes at minimum capacity. So you at least have two data points. Occasionally you're going to want a third or fourth kind of to figure out what your curve looks like between them. It sounds to me like the person asking the question was getting maybe some backwards air coming in the exhaust to help over this way because the return fan was running so slow. And I have definitely seen that. I've seen where the exhaust is another intake, and you're sucking air in here, you're sucking air in here, all of which because the supply fan's working hard and the return is not working enough. That tells me that we're not asking this return fan to do enough work. It means we may be asking to leave too much air in the building. It may mean we have an issue with where we're measuring our building pressure, sensing location, accuracy, calibration, etc. That's not a healthy condition if the return is doing so little that you're sucking air in the exhaust. And that's where you want to get into that troubleshooting mode and say, well, is it doing that all the time, under all modes? Is it only doing that when we're at minimum versus maximum, etc.? So cause for further investigation.
Yeah, and John, he did mention as you were talking that the supply fan was drawing the air in through the relief duct because the return fan wasn't creating enough positive pressure in the relief duct.
Right. So I think I guessed close enough. So yeah, I can't give you the magic formula, but you definitely need to start looking at what is the data. When does this happen? Is it when I'm only at 100% mode? Is it when I'm at minimum mode? How has this offset between the two been determined? And overlay the pressurization trending to say, what does my pressurization look like? Again, I would go into full troubleshooting mode with what's the range of the sensor? How is the outside port being measured? If it's a stormy, windy day versus a not windy day, I mean, you want to kind of get some references here and go into troubleshooting mode because that's not healthy.
Okay, and we have had a few other comments that came in through that, but I'm going to send those to you after, and maybe we can have kind of a little follow-up, but I wanted to get to a couple other questions that came in, if I could. And that is, this related to slide, I believe, 21. Did you drive the duct static by opening the respective VAV boxes or just increase duct static pressure set point?
Okay, so we accomplish this table by using the VAV boxes. To answer your question, this was not done in disregard to the actual system. So what we actually did was we started with the system all the way down at minimum, so all the boxes were down at minimum, and that translated to right about your 50% speed. And then we opened some more VAV boxes, and we said, okay, great. So we were actually what was happening, so if you can imagine, we had the balancer with us, we had the controls contractor with us, and then we were basically orchestrating and saying, okay, open some more boxes. This is one where they actually specified whatever, the 1, 2, 3, 4, 5, 6, 7. This was a 7-point plot. It was actually specified to plot out the 7 points. So we were using the VAV boxes, the real system. It was not just overriding the supply fan to do this. So we were getting, I'm going to say, pretty realistic data of how the system will perform. And that's a great question.
Great. Thank you, John. Another one is, one of the slides cautioned against linking EA, OA, and RA dampers. Why is that?
Okay. The quick answer is, if you go through the math here on the right, what you're going to see is the example I'm using is we're in min OA mode. So that would be, this would be at 4578, okay, which is the value on the table. We are not in economizer mode. In this example, I'm using this data here on the right. We're not in economizer. This damper would be closed. However, if you go through this example, we only need a certain amount of recirc air coming down this duct, okay, of 732. We need to exhaust some air. We need to relieve some air. And my caution here is, if this is closed, but yet this needs to be cracked open and it's all a single output, you're going to run into trouble. So good question, kind of going back. I may have gone through that too quickly. You can find yourself, when you start dealing with building pressurization, you're starting to try to drive the system to a slightly higher level of performance that is not going to be achievable when you link these dampers as a single output. So if you're doing a design review, I would say, or even a control submittal review, depending on where you come in the project, crunch these numbers, try to get a handle on this, and then look at what the controls contractor did. If they're using a single output, if you're not in economizer mode, what is the values you're going to be seeing? And if you need to, like I came up with, I need to relieve 1800 CFM of air, you're going to be like, the damper's going to leak enough for me to do that, or do I actually need to crack those things open? So that is why.
Okay, thank you, John. I'm going to try to get one more question in, but like I said, there's been several that have come in, so if you're fine with getting these questions after and following up, that would be great. It says, have you had experience with modulating the RA fan speed to maintain a slightly positive RA discharge plenum static?
Yes, and that's a good question. Yeah, they're talking about maintaining a positive pressure over here, so that way you don't draw in air over here. I'm going to say that is always a challenge. Where's my little caution symbol? If you see that, just caution, know you've got some headaches ahead of you. It does work. You can get it to work, but again, you're measuring very small pressures. So now you really have to get into the accuracy of that sensing device. You're using that as real-time feedback for these return fans. Loop tuning of these return fans is really critical. It's a challenge to do that. I'm going to say that's probably the least favorite of all my ways to do this. The simplest being establishing some fan tracking. Let me just go back to a different slide here. Yeah, the easiest is fan tracking of some fashion, whether it's percent or hertz, coming up with some fan tracking there. The next that's the easiest. If you have airflow stations, you can then say to this return fan, well, I want you to control to this amount of air over here, and you can control that. That's a lot easier than if you were to basically add a static pressure sensor, add another one. What they're saying, the question is, if we add one of these over here, okay, and control to a slightly positive pressure, I've seen it, we've done it, it's just finicky. It's a little bit of a challenge to do that. Again, and if you have that, just make sure you're testing the max, the min, and the modes in between there to make sure that you figure out what that needs to be. You should have the return fan tracking to that pressure, but it's going to be a very small number, 0.01, 0.03, something very small. So again, you're measuring a real small value.
Great. Thank you, John. And thank you, everyone. As I mentioned, I'll make sure John gets the rest of these questions, and he'll follow up with you. We really appreciate you, John, your time and expertise. And on behalf of the BCA, I would like to thank everyone for your participation in today's Tech Talk. Have a great day.
Thank you, everyone.